Hello everyone. Now I am explaining about fillet weld problem, another example problem by using this data. So we are having the data, that is web plate. This is the web plate 1000 mm by 12 mm, and this is the flange plate, that is 400 mm by 20 mm, and flange cover plate, that is 375 mm by 16 mm, and shear force, that is V equal to 1000 kilonewtons. So by using fillet weld, we need to connect these three plates. This red color portion is the welding portion. So flange cover plate is connected to flange plate, and this flange plate is connected to this web portion. Okay. So and first now we are going to calculate the stress in the weld. So stress in the weld is we are having the formula. The code specifies that Fu by root 3 gamma mW, that is page number 79, clause number 10.5.7. I will show it now. So this is 10.5.7, the design stress in the welds. So we are using the formula Fu by root 3 into gamma mW. So same formula I wrote here. So Fu value is ultimate stress, you already know that, 410 by Fu value is this value is available in table number 1. So root 3 into gamma mW partial safety factor, that is table number 5, page number 30, it is available. So after that I solved the equation, I got 189.37 Newton per mm square. Next we need to find out the minimum size of the weld. So minimum size of the weld is 5 mm, already code specifies in table 21, this value is available. So code specifies that we need to take the minimum size of the weld is 5 mm. Next, maximum size of the weld. So maximum size of the weld means the thickness of the plate, web plate. The thickness of the web plate is 12 mm. So code is specifying that we need to subtract 1.5, that is here 10.5.8.1. The code specifies that where a fillet weld is applied to square edge of the part, the specified size of the weld should generally be at least 1.5 mm less than the edge thickness. So the thickness is 12 mm. So the code is specifying that we need to taking less than 1.5. That means we need to subtract minus 1.5. So I got 10.5. So now we need to assume the size of the weld, that is in between 5 mm to 10.5 mm. I assume that 7 mm. Okay. After that, right now we found that shear stress in the weld. After that, we need to find out effective throat thickness. Effective throat thickness means we already familiar with the throat thickness. Throat thickness means here you see the welds. This is the welding portion, and this is the welding portion. Suppose our weld is like this. This is the throat thickness from this point to here. This is the throat thickness. Okay, T equal to 0.7 into S. This formula is specified by code, 0.7 times the size of the weld. So our size of the weld is 7, that is we assume the size S equal to 7, 4.9. Summation of T. Why we are multiplying with 2 is, actually we are doing the welding in both sides. Here both sides we are doing welding, that's why I multiplied with 2 mm, multiplied with 2, that is 2 into 4.9, that is 9.8 mm. Okay, after that we need to find out shear stress at the junction. In previous we found that shear stress at the weld, now shear stress at the junction. In this junction, what is the shear stress? In the junction portion. Junction means this is the junction. This is the junction and this is the junction. In this junction, what is the shear stress we need to find? So for that we are having the formula tau 1 equal to V into AY bar by IXX into summation of TE. So V value already given, that is 1000. We need to find out A into Y bar. A is area of the flange plate. I am taking for 2 plates area, that is 400 into 20, L into B. Okay, for this plate I am calculating the A into Y bar. A means area, L into B. L is 400 value, we know that. B is this value, L into B 400 into 20, and after that Y bar. Y bar means 500 for this plate. I am telling about the flange plate. 500 means centroid of this for this plate. So from here to here it is 500 distance, that is 1000 by 2, plus we need to calculate the centroid. Centroid means 20 by 2. Centroid of this plate is 20 by 2. So that's why I wrote here 500 plus 10. 20 by 2 is 10. Okay, like that I am calculating the same to cover plate. 375 into 16 is area, and 500 is the web plate, centroid of this web plate. This is 500 plus 20 of this plate. Now we are calculating centroid for this plate. So from here to here 500, from here to here 20, plus 16 by 2, that is 8 centroid. So that's why I wrote it as 500 plus 20 plus 8. So total I got 724.10 power 4, 724.8 into 10 power 4 mm cube. Like that, after we are going to calculate Ixx. Ixx is moment of inertia of the xx axis. So already we know the formula for rectangle BDQ by 12, moment of inertia formula BDQ by 12 plus AYC square. So like that we are having 3 plates for cover plate, flange plate and web plate. That's why I wrote here for your understanding sake, that is YC square is cover plate, YF square is flange plate and DW is web plate. So for that B value we know that 375, L into D cube, that is depth 16 cube. A value already we know that 375 into 16, L into B. So YC square already we calculated here 528. So similarly like that I calculated for flange plate, like that web plate. So web plate is 12 into 10 cube by 12. Okay, this is depth of the web. After that I got the value 8.507 into 10 power 9 mm power 4. So I substituted all the values in this equation. So I got the value 86.93 Newton per mm square. So this is less than stress in the weld. So shear stress in the junction is less than shear stress in the weld. Okay, 189.37 is shear stress in the weld. Like that, up to now we calculated this portion, this junction portion. Now we are going to calculate this portion. Okay, flange cover plate to cover plate. That's why I wrote here connection of flange plate to cover plate. So same formula using A into Y bar for flange cover plate, that is 375 into 16 mm is area, 528 already I told you. So after calculating this I got the value. So same equation I substituted the values, tau 2 equal to, same equation I used this 1000 we know that. So substitute all the values, I got 37.99 Newton per mm square, that is less than 189.37 Newton per mm square. This is our shear stress in the weld. Okay, so less than shear stress in the weld means our design is safe, hence our welding is safe. Okay, thank you, thanks for watching.